Okay, we're ready to go. So we had lesson 4.2, Rolle's theorem and the mean value theorem. Are there questions on the previous assignment? Any questions from 4.2? Not hearing any. So actually we have a pretty, I believe, very straightforward lesson for today. 4.3, when is a function increasing and when is it decreasing? And this is, it really doesn't get much simpler than this. When a function's increasing, it's heading uphill. And when it's decreasing, it's heading downhill. So if we look at this picture, you see in the diagram below, like I said, if it's going downhill, it's what's true of its derivative when a function is going downhill? The derivative will be less than 0, negative. When it's constant, the derivative will be 0. And when it's going uphill, the derivative will be positive. So really, all we need to do to look at increasing or decreasing is the sign of the derivative. So, welcome, Devin. All right, let's take a look at an example problem. A very easy one is f of x equals x squared. Very familiar function. It's a nice parabola. I've got a picture of it on the right. And it's got a really simple derivative, 2x. Now, when will, one thing I didn't write on here is, when will the derivative be 0? So when does 2x equal 0? Obviously, when x is 0. And hence, that point off to the right there that I've marked, I'll just mark it again, make it a little bit darker. That point is 0. And at that point, the derivative is 0. So that divides the graph into two parts, the part to the left of that, the part to the right of it. To the left of it, you can see we're in negative territory for x. And I just took a sample, pick a negative point like -1. What's f of -1? I'm sorry, what's f prime at -1? 2 times -1, -2. It's negative, which tells me that, to the left of 0, our graph is decreasing. To the right of 0, I picked a sample again, 1. What's f prime at 1? 2 times 1 is 2. It's positive. So this is pretty simple. And to the left of 0, it's decreasing. To the right of 0, it's increasing. And if you look at this answer over here, that's in interval notation. It's saying this thing is increasing from 0 to infinity, and it's decreasing from -infinity up to 0 in interval notation. So I know this is pretty simple stuff. At least, especially with this function, it's very straightforward. Are there any questions here before I move on? So some real simple guidelines for you. We did something like this for you last time too. And that is, the first thing you got to do is you got to find the critical numbers. So this is not new. Find the critical numbers, because at the critical numbers, that's where the derivative most likely will be 0. And then that becomes a dividing post for on either side. What's happening on the left side of that? What's happening on the right side of that? Then number 2 says, once you've got those critical points, determine the sign of the derivative at what one test value. You can pick the value on either side. And then if it's negative, it's decreasing. If it's positive, it's increasing. Let's take a look at another example here. So let me make this bigger for you. So this time we have the function 1/2 x minus sine x. And we want to do that for the interval from 0 to 2 pi. Okay? So what's the first step? If we're going to find critical numbers, we have to find the first derivative. What's the derivative of 1/2 x? 1/2 in the box here. And what's the derivative of minus sine x? The derivative of sine is cosine, so just minus cosine x. So there's our derivative. And when is that equal to 0? So we set it equal to 0. We solve. It comes down to when is the cosine of an angle 1/2? And that's what? Cosine of 1/2, that's 60 degrees. And that's pi over 3 in radians. There's another place where the cosine is positive, not just in the first quadrant, but also in the what? In the second quadrant. What's a 60-degree angle in the second quadrant? So again, we have 2 pi minus pi over 3, 5 pi over 3. So we have two critical values here. Pi over 3, 5 pi over 3. Now, I kind of think of it like those are fence posts. So we have pi over 3, 5 pi over 3 in this chart. So we've got everything to the left of pi over 3. We've got pi over between pi over 3 and 5 pi over 3. And then we have everything to the right of pi over 3. So we have 3 zones that we need to check out. So first, to the left of pi over 3, what's an angle smaller than pi? Pi over 3 is 60 degrees. Smaller than that would be, well, they picked 45. What's the derivative at pi over 4? So derivative is 1/2 minus the cosine of x. What's the cosine of pi over 4? Cosine of 45 degrees is 1 over the square root of 2. Okay? 1 over the square root of 2 subtracted from 1/2. 1/2 is 0.5. 1 over the square root of 2 is less than that. I'm sorry, is greater than that. And so you're going to wind up with a negative. And because that's negative, that tells me this whole zone to the left of pi over 3 is going to be decreasing because the first derivative, even though we only did it at a test value, that tells me that the first part of this has got to be decreasing. Then pick an angle between pi over 3 and 5 pi over 3. So I got to just check here. So they picked pi over 3 is 60, 5 pi over 3, that's 1 2/3 pi. So that's in the, I got to just think here. By the way, I do apologize. I said that was in the second quadrant. Cosine is positive in the fourth quadrant. First quadrant, fourth quadrant. So this 5 pi over 3 is that's that 60-degree angle in the fourth quadrant. So what's an angle between pi over 3 and 1 2/3 pi? 1 pi. Okay, let's use that as our test value. What's 1/2 minus the cosine of pi? Well, the cosine of pi is 0. Let me think. Cosine of pi radians. Cosine is that's -1. And 1/2 minus a -1 is positive 1.5. It's positive. Therefore, it's increasing. And then finally, you're supposed to pick an angle bigger than 5 pi over 3 and less than 2 pi. So they picked 1 3/4 pi. And when you take that derivative, let's see, that's a 60-degree angle in the fourth. Let me think. What angle is that? 1 3/4 pi. Well, anyway, when you do it, when you work it out, that turns out to be a negative, and so it's decreasing. Now, if you take a look at that graph, 1/2 x minus sine x. Let's take a look at that. 1/2 x minus sine x. So, and we're going for, I got to change my labels. Let's put step pi over 2 in here. And where are we going between? You're going between 0 and 2 pi, okay? Between 0 and 2 pi. So from here up to here. And we found critical values at what? We found them at pi over 3 and 5 pi over 3. So let's just go back and look. Pi over 3, right about in here. And 5 pi over 3, that would be this value. Before pi over 3, it is decreasing. After pi over 3, between 5 pi over 3 and 5 pi over 3 in this area, it is increasing. And then between 5 pi over 3 and 2 pi, it's decreasing. And that's what we found out down here. I mean, we didn't write it in interval notation, but oh yeah, and here's the graph. I didn't realize. Okay, we got the graph right there. Okay, let's take a look at another one. This one looks like this. Let me do a little erasing here. And then we can talk about this. Okay, so we got a clean slate. So this time our function is x to the 4th plus 1 over x squared. All right. Well, it's not a very good format. We could break that down as follows. We could say x to the 4th over x squared plus 1 over x squared. Do you see how I did that? I went backwards and broke it into two separate, they're both the same denominator. And then, what's x to the 4th over x squared? That's x squared. And x1 over x squared we could think of as x to the negative 2 power. So that's how they got right there. Okay. Now, what's the derivative? 2x minus negative 2x to the negative 3rd power. Okay? That's written in, if we get rid of the negative exponent, it's written like that. And then if we get a common denominator, it's written like that. X to the 4th can be written as what? X squared minus 1 times x squared plus 1. It's the difference of two squares. And x squared minus 1 can be broken down further as x plus 1, x minus 1. So here it is with the numerator completely factored. Now, when is that equal to 0? Because that's we have to find critical points. Only when the numerator is 0, correct? When a fraction is equal to 0, only when the numerator is. So on the top, when is 2 equal to 0? Never. When is x squared plus 1 equal to 0? Anybody? When is x squared plus 1 equal to 0?
Can it? I don't think it can be equal to 0, because if you try to do like -1 squared, then it just goes to 1, because any negative number squared is a positive, so it can't equal 0.
Yeah, Sam, you are exactly correct. So that can't be 0. Okay, so what's the next factor? X minus 1. When can that be 0? Well, that's easy. When it's 1. And when can x plus 1 be 0? When it's -1. So do you see how we just came up with these two right here as critical points? Plus and minus 1. Where did they get x equals 0 from? This one. Don't forget, what's the other thing you have to check when you're checking for critical points? And that's when the derivative could be undefined. And if you look up here, if x is 0, what happens to that denominator right there? It becomes 0, and then you have an undefined. So do you see how we came up with 3 critical points? If you're a little bit lazy, I don't mean that, I didn't mean lazy, but if you're a little bit lackadaisical, you might have missed that 0. So watch out. Okay, so we've got 3 points, 3 critical points. So we have 3 fence posts, so to speak. So I'm going to just write them in here. Here's the one at -1. I need my pen. Here's the one at -1. Then we've got the one at 0. And then here's the one at +1. Okay, so do you see how we have to look 3 places here? To the left of -1, between -1 and 0, and between 0 and +1. And after. So we actually have 1, 2, we actually have 4 locations here. All right, so first of all, left of -1. Well, let's pick a test point. They picked -2. What's the derivative at -2? Now you got to go back to this derivative. It's a little bit long, but you got to work it out. Let's do it real quickly. You plug it, you got a 2. Then you got -2 squared plus 1, which is what? 5. Then you've got -2 minus 1, which is -3. And then you've got -2 plus 1, which is -1. And when you multiply that, can you all see? Let's see. What did I do? Oh, did I do that right? -2 squared is 4 plus 1 is 5. That's a negative. -2, that's a negative. Okay, what I'm doing, and that's over a negative, because I forgot to do the denominator. What's -2 cubed? -8. So on top we get a positive, on the bottom we get a negative, and a positive divided by a negative is a negative. Therefore, our test point turned out to have a negative derivative, therefore it is decreasing in that section. Okay, then anyway, each section you have to plug into your derivative, this thing up here in this that I'm circling right now. You got to plug it in there and see what you get. And if you get a negative, it's decreasing. If you get a positive, it's increasing. And you see how we get, in this case, decreasing, increasing, decreasing, increasing. And if we look at the graph, they've got it. They've kind of got it here to the, yeah, there it is. You can see our critical points are -1. That's right there. 0, it's at the asymptote, and +1. So, yeah, in between -1 and 0, it's increasing. In between 0 and +1, it's decreasing. You can see that the increasing, decreasing is correct. You guys can speak up, ask questions if you want, please. All right, so let's look at, oh yeah, so here's the beginning of the assignment. Okay, and the assignment gives you the first couple they give you are just looking at a graph. So look at number 1, please. Okay, you can see we have this graph there. What's the largest interval on which the function is increasing? From where to where? Where's the longest interval in number 1 where it's increasing?
Would it be from 0 to 6?
Yeah, that's what it would be. Yep. And what's the largest interval for number 1 where it's decreasing? Well, it's decreasing from 6 to 8, and it's also decreasing what, from 9 to 10? So 6 to 8 would be the longest decreasing one. Okay. All right, you get the idea there. So they're just getting you into the mood there. Some more visual problems. So it says on numbers 3 to 8, use the graph to estimate where do you think this thing is decreasing. You can see in number 3, it's decreasing from what? Negative infinity up to 3. And it's increasing from 3 up to positive infinity. And then if I asked you to actually do it, what would you do? How would you proceed to do this? Instead of just eyeballing it, you would take the derivative, find the critical points, and then do the kind of thing we were just doing before. By the way, so if you do let's just do number 3 the long way. Okay. Let me move this over a little bit. Okay. So you would take the derivative of that, which is 2x minus 6. You would set that equal to 0. You would solve. And just like we thought, 3 is a critical point. That's exactly, we could see that before. And then you pick everything to the left of 3. So take an example. What's f prime at, for example, 2? 2 is to the left of 3. F prime of 2 is 4 minus 6, negative 2. It's negative. That tells me decreasing to the left. And if you take a sample point to the right, like f prime at what? 4, you get positive 2. And because it's positive, it's increasing. So the graph supports. So, okay, no big deal. All right. Yeah, and we've really gone through this. Let's just go through it one more time. So what do you do to find out where a function is increasing or decreasing? Step 1, find the critical numbers. Don't forget about the critical numbers that might come up when the derivative is undefined. Then set up intervals. Okay, so if you only have 1 critical point, then you only have 2 intervals, left and right. If you have 2 critical points, that's going to divide it into 3 areas. If you had 3 critical points, that gives you 4 areas, etc. Then simply pick a test value in each of those intervals, calculate the derivative at that test value, negative, decreasing, positive, increasing. So pretty straightforward. Okay. We did that one. I got a little bit lost here. My apologies. Okay, let's just take a look at these directions. When you get to 21 to 44, it says, applying the, let me make that a little bit bigger. Applying the first derivative test. Find the critical numbers, if any. Find the intervals that are increasing or decreasing. Apply the first derivative test to find out if they're if there's any extrema, and use a graphing utility to check your results. So all it's saying here is when you get done, check out Desmos or whichever technique you would like to show that your findings are correct. So let me see. So let's take a look. I'm just throwing out a few examples to look at here. Let's take a look at number 17. Okay, 17, we have e to the negative x plus e to the 3x. Step 1, find derivative. You get my derivative there? Why is that negative e to the negative x? Because of the chain rule, right? Because you got to multiply by -1. Okay, and then the second part, what's the derivative of e to the 3x? Well, it's e to the 3x, but then you have the chain rule times 3, so I put that 3 in the front. Okay, so now when will that derivative be equal to 0? So I did a little bit of algebra there, and I came up with, let me explain how I went. So everybody should see how I got down to here, right? I'm thinking, so how do I solve that? Well, I could do the natural log of both sides, because that'll get rid of that e base. The natural log of both sides, the natural log of the left, natural log of 1/3, equals the natural log of the right, 4x. And now I can actually solve for x. You can do natural log of 1/3 on your calculator. So we can come up with a value. We found one critical point this time. Because of the nature of this problem, it turned out to be a decimal. All right, let's take, anybody have a question there? Let's take a look at number 19. This one got a little bit of a challenge to it. We have x squared times the natural log of x over 2. We always seem to have a little bit of trouble with natural logs. So this is a product. X squared multiplied by the natural log of x over 2. So I got to do the product rule. The first times the derivative of the second. So what do you do when you take the derivative of a natural log? You take 1 over that thing. What's the reciprocal of x over 2? 2 over x. And then we have a chain rule, because the derivative of 1/2 x is 1/2 plus the second times the derivative of the first. So these, the 2's cancel. Let's see. The x squared, so x squared times x is x. And then we got this 2x from way over on the right comes in. Natural log stays the same. I factored in x. We have two terms, x and 2x times the natural log of x over 2. I factored out an x. Why? Because we need to set the derivative equal to 0 and solve it. And whenever you have something equal to 0, you want to think factoring. So there's one source of a 0. X could be 0. And this thing over here could be 0. So I got to work on that. How do I get 1 plus 2 times the natural log of x over 2 to equal 0? That's over here at the right. Subtracted 1 from both sides. Divided both sides by 2. Okay. So let me explain. So how did I get from here to the step below that? Well, the natural log of x over 2 means that when you take e to the negative 1/2 power, you're going to get x. The natural log of something is equal to something. That means that negative 1/2 is the exponent on e that will give you that. So e to the negative 1/2. equals x over 2. E to the negative 1/2 means 1 over the square root of e, multiply both sides by 2, and you can get a decimal out of that, 1.213. So remember, don't forget, we got 0 too. So we found our second. So one of the critical points is 0. The other one is 1.213. So now that divides. So we've got 2 points. What about to the left of 0? Well, here's the problem with the left of 0. Take a sample negative number left of 0, like -1. Okay. What's the natural log of negative 1/2? The problem is you can't take the natural log of any negative number, because e to no power on earth will ever equal a negative. So what I'm saying here is, at the bottom, when we investigated to the left of 0 here, we found out there can't be any negatives. So I wrote can't be. All right, so let's look at the next interval, between 0 and 1.213. So we could pick a number like 1 and go ahead and calculate, see if you get a positive or a negative in the derivative. What would I use for my derivative? Maybe this line right here. Plug in a 1 there. And what do you get? 1. Here, let me write this out. So you get 1 plus 2 times the natural log of 1/2. Okay. And that's, all right, what did I do? I have to look. What did I miss? 1 plus 2 times 1 is 2 times the natural log of 1/2. What's the natural log of 1/2? Yeah, that's a negative. So you've got 1 plus 2 times negative 0.7 approximately. That's 1 plus a negative 1.4. And do you see that turns out to be negative? So hence, down here at the bottom, that tells me that interval we're decreasing. Anyway, and then finally pick a number larger. So for this last interval, pick something like 2, and you will see that that turns out to be positive, and it's increasing. Then let's take a look at what the graph looks like for that. Okay, x squared times the natural log of x over 2. Okay, I don't have that one up here. X squared times natural log of, what was it, x over 2? Yeah. And let's check out. We found out that the critical points were at 0 and 1.213. Okay. By the way, do you see that it doesn't go to the left of 0, just like we said? Okay. So I got to change my x-axis labels again. Whoop. I got to change those. Let's get rid of the step for pi. There. Okay. So what is this? That's the 1.213 critical number. Yep. And 0 is obviously a critical number. And you can see that, what did we say? In the first interval, there was nothing happening because there was nothing negative. Between 0 and 1.3, it's decreasing. So right in here, it's decreasing. And between 1.3 forever, it is increasing. So the graph supports the work that we did. All right. Yeah, let's take a look at numbers. Let's take a look at this one. This section toward the end of the assignment says use a computer algebra system to differ. So here it's actually saying use something like Desmos to differentiate. So I want to show you how to do that. So I want to take 66, this function, 10 times the quantity, 50 minus the square root of x squared minus 3x plus 16, and do it in the interval from 0 to 5. Okay. That's this guy. Okay, so you can see it's a parabola. All right? And we're going to do it from 0 to 5. So we're doing it from, from there to there. Okay, from 0 to 5. Now, a trick you can do in Desmos is instead of just putting in the equation, do you see how I put f of x in the beginning? I said f of x equals. And then all you need to do to find the derivative is what I wrote below it, f prime of x. Bingo, you've got the graph of your derivative. Now, let's analyze this a little bit. Critical numbers is when the derivative is undefined. Well, does the derivative look undefined? No, the blue looks perfectly continuous, no problem. When is the derivative 0? Yeah, at 1.5. Do you see that? What should happen when the derivative is 0? We should meet a max or a min. Sure enough, 1.5. You see how we're at the top? So that makes sense. Why is the derivative 0 there? Because we're at a critical point. So one more time. So when you've got a function like this, that'll give you the graph. But if you put in the beginning of it, f of x equals, you'll get the same graph, and then you can just, this is really cool, you can just define the derivative, just put f prime of x. Talk about an easy derivative. There it is in blue. Okay, so hopefully you see, I know it doesn't look like the derivative has a relationship to the original. They look like totally unrelated, and yet you can see that when the derivative is 0, that is a very important critical point on the red graph on the original function. So that's kind of pictorially what's happening there. Okay, so let's see, what do I got from, let's go to the assignment. Core exercises. So the 4.3 is the assignment. That's on the website, so no surprise there. And you can, I hope I think you're seeing that we're seeing a lot of repetition. I mean, what, all 3 lessons so far in chapter 4 have been about critical numbers, haven't they? Yeah, we're going to be stuck on that. And so that process is important. Being able to take a first derivative, finding out when that first derivative is 0, or when that first derivative might be undefined. And then, hey, is the first derivative negative, positive, or 0? And that tells you if it's increasing, decreasing, increasing, or constant. Questions? You can let me know later. If you're working on a problem, you get stuck. Don't forget, you can do a text message or an email, and I'll do my best to respond as quickly as I can. Okay, thanks. I hope you have a good rest of your Tuesday.